Coulomb squared per meter squared. I prefer K just because it's easier when we're doing Coulomb's law and I mean all those equations, but some textbooks just immediately use 1 over 4 pi epsilon naught instead of K. And the fourth equation, so this is Ampere's law was that, Maxwell added this, and then we have the sum around the loop of E dot L. This is Faraday and Lentz's law, is equal to the negative change in the magnetic flux over time. And this E dot L is just the voltage. All right, so this is, Maxwell adds his little bit, and then he starts going, what if I had a charge sitting right there? It has its electric field. Let's just assume for the sake of some standard here, we'll just assume it's positive. So I have an electric field that goes away from it. It's not moving, so there's no magnetic field. There's no change in the electric flux. If I'm here as an observer, the electric field hitting me doesn't change. My electric flux doesn't change, and so that part is irrelevant. There's no moving charge, so that part doesn't work, and so no magnetic field is created. But I'm going to take that charge and I'm going to move it over here. So now my electric field is going to be going, well, it obviously moved. So if I'm here observing it, I have the electric field going this way, and then the electric field switches its direction as the charge moves. If that's the case, then I will have a change in the electric flux hitting me. So if I have a change in my electric flux, I'm going to create a magnetic field. Now, before we looked at this as I have a moving charge, therefore I have a current, therefore I have a magnetic field. But this is just a different way of looking at the same thing. Now, if I take the charge and I bring it over here and then I take it back, my electric field changes, creating a magnetic field. But how much my electric field changes depends upon which 2 points in time I'm looking at. So if my electric field changes by moving it back and forth, my electric field changes, well, every time it changes, it creates a magnetic field, but my magnetic field is going to change also. Because my electric field is, it's here, it gets faster, it slows down, then it goes back the other direction. It's like having an alternating current. So I have a change in my electric field, which creates a magnetic field. But my magnetic field is changing, so my magnetic flux is changing, which is going to create an electric field. So I have a change in an electric field, which creates a magnetic field. Let me stick in the intermediate step, which creates a change in the electric flux, which creates a magnetic field. If I change how that changes, that's going to change my magnetic field, which means that I will have a change in my magnetic flux, which means I will create an electric field.
Is that a correct notation, the delta something?
Sure. That's correct notation.
And then it just repeats.
And so if I had a change in the change this change in the electric field would cause a change in the electric flux, which creates a magnetic field. So if I had this particles oscillating back and forth regularly, what's happening here is that there's constant change going on. So my electric field creates a magnetic field, which creates an electric field, which creates a magnetic field, which creates an electric field, which creates a magnetic field, and so on. So given this pattern here, all I have to do is get my electromagnetic wave going, and it will self-propagate. So if I have an electric field cruising along, so if that's my electric field, that's constantly changing, it's going to create a magnetic field that is also constantly changing. And we will see how well I do with a three-dimensional drawing here. So if I imagine my electric field is oscillating back and forth in the plane of the board here, the magnetic field is going to change towards us and away from us, so I will try to represent that as,
So what you're saying is like if we have the electric field,
electric field.
yeah, going like this, the magnetic field's gonna go like this.
Yep.
Okay.
So magnetic field in and out of the board, electric field parallel to the board. So all I have to do is get it started, and it will continue on itself. So what Maxwell did is he took those last two equations, the one that creates a cycle, and he calculated what the speed of an electromagnetic wave is. And the implications of this, basically, there are two major shatters to classical physics that happened in the early 1900s. One of them stems directly from this. The other one stems from a separate thing. But what we'll do, I guess, on Monday is we will derive the speed of an electromagnetic wave, talk about the implications, and that's going to lead directly into special relativity, which is the first major step in trying to teach you that all the stuff that you've learned up till now is just a little bit off. Okay, half the stuff you've learned up till now is just a little bit off. Give it enough time, and I think we will have enough time, then we'll get into the other part, which basically should shatter any semblance of what is real in your head. And that is the really cool stuff in physics.
What was the other breakthrough?
Quantum physics.
Yep, quarks and Einstein.
Yes.
Fake stuff.
What was that?
Fake stuff.
How dare you? You know, there are some people who do consider, there's the notion that anyone who does the same thing twice and expects different results is insane. Physicists in the quantum world, you can do the exact same thing twice and get different results. So insane people and physicists. We'll say there's some absolutely great quotes. I will talk. So many thoughts are running through my head. It's a question of, do you get different results because of something known as hidden variables? So that there is a fundamental difference between two objects. So you get different results because of something we can't see, or is it just random? That it's going to either go one way or the other, and there's nothing to really indicate why it should do one or the other. It's just that's the randomness of the universe, and therefore we will, it makes life a little less predicted. If you've heard the Einstein quotation of God doesn't throw dice, I got at least one nod on that one. That is in reference to that it's the randomness of if I roll dice. If it's an even number, it's going to go this way. I know it's going to go that way. But there's some really, really funky things. Oh, let me just give you another sneak preview here. If I've got a wall with two slits in it, and I send water waves towards it, then the water waves are going to basically go through each of these little grooves here, and these two waves will overlap. So you'll have points where with constructive interference and points with destructive interference. So if I were looking at how the waves hit the wall over here, most be the biggest wave here, and then they cancel out, and it'll look something like that.
Almost looks like,
Sorry,
I don't know, it just looks familiar.
double slit experiment.
No, like what it looks like, the wave.
Okay. At 2 in the morning when you think of it. All right.
Yeah.
So, if I do the same thing with light, and this was the big thing in, it was Newton versus, I think it was Huygens, whether light was a particle or whether it was a wave. There was a famous experiment where light was set at it, and then over here, it's brightest here in the middle, and then less so, and this was the big piece of evidence that says light is a wave. The cool thing is, if I then have a detector here so I know which slot the light went through, the pattern changes. So if I observe so it's either going to go through here, or if it doesn't, I know it goes through there. If it does, so if you have the detector there, then you get one there and one there. You don't get the wave pattern anymore. You get a particle pattern. And I'll leave you on that note.
So they're both right,
Yes.
but they're both wrong.
Newton did come up with a term which never quite stuck, but he did at one point use the term waveable.
Wave.
And then later on, they said, well, if light behaves like a particle sometimes and a wave sometimes, what about electrons? Do electrons behave like one thing or the other?
And so on and so on.
And it turns out, we all do. Called wave-particle duality, but that is for definitely another day.